using what you guys know from the previous 5 units of physics, what's the maximum speed I can travel over the top without losing contact with the ramp? You should look in your notes. We've done this problem about a dozen times. So I'd like to know the maximum speed that this object can travel over the top of this hill without losing contact with the hill. Good luck. That's the clue. Anything traveling in a circular path has to have this condition met. That has to be the condition met. And every part of this has purpose, meaning you have an entire procedure on how to construct the left side. Free body diagram, draw some arrows, stuff like that. You have a procedure. And you have a procedure on how to deal with AC. There's a procedure, a specific substitution that is always done in the circumstances where you have centripetal acceleration. So we're not helpless. We have a plan. We have something to do here. So start with your free body diagram and work your way through this problem. There's nothing different about this because it's rolling than when it was sliding first semester. Start with a normal force going up. Anything else? All right, so you gotta help me out here. When I draw this arrow, it's supposed to represent the weight of the object. Is that gonna be an arrow that is smaller than a normal force, same size as a normal force, or bigger than a normal force? And before you answer, now that you thought about it for a second, look, everybody in the room, I hear you whispering. You should be thoughtful about this. And I'm not trying to trick you. Is this a first law problem or a second law problem? So one of these has to be bigger than the other. So anybody just now who just said same size, you're wrong. And again, I'm not trying to rub your face in it. I'm saying you have a clue that tells you these need to be unbalanced. And moreover, there's more to that clue. Do you remember the other part? So let's see. I'm sorry, Johnny, we're back to you. Bigger or smaller? That's as good a way to say it as anything else. The downward force has to be bigger because the unbalanced force has to be towards the center of curvature. And the center of curvature is here. So I need more force downwards than upwards. That's perfect. Also, if you don't have this in your notes, you're going to have to put together a relationship, right? Net force, which means you're going to add these two forces together, making one of them positive and one of them negative. Make a decision. I want to see what you write on the left side of this equation. Your downward should be positive. We want to make the direction of the acceleration downwards because that's the direction it has to accelerate. So it's best to make downwards the positive direction. That means we're going to have mg minus normal force. That's the left side. Now, there might be other forces acting on this system. We didn't bring it up. But, I mean, if it's spinning and moving at the same time and we say that it's rolling, well, there's probably a frictional force acting on it. But that frictional force is going to be left or right. And that's not going to contribute in any way to the net force for centripetal acceleration, which has to be towards the center. The friction has to be, unfortunately, it has to be tangent to the curve, which means it can't be towards the center. That's a definition kind of thing for geometry. So these are the two forces that contribute. Now you have to work on the other side, which means I need to call on somebody here. Johnny was very helpful. Wow, we're not going to move very much. 19. Where's 19? Sorry, kiddo. What do I put in for A? See? Oh, excellent. V squared over R. How smart are you feeling today? No. Because I'm going to ask you some more questions. I think I can ask you at least one more question. Are you ready? I want to walk through this relationship because you were asked to find something about V, right? How big can V be? Which of these letters is the same regardless of how fast we're traveling? We're just going to go through each letter. And any letter that is the same, regardless how fast we're traveling, I'm going to color red, okay? For example, the mass of the rolling thing. Does that get bigger or smaller if it goes faster? So we know that that doesn't have anything to do with how fast it's going. How about G? Does G have anything to do with how fast it's going? No. Will G change if the object goes faster? Okay. How about the normal force? Will the normal force have anything to do with how fast it's going? Betty, why are you saying yes? I'm not trying to be hard here, guys, because you're right, Betty. The normal force does change if you're changing speed. It's the only thing that can. Look at everything else in here. Look at the other side of the equation. The other side has m in it. That can't change if you go faster. Can the radius change if you go faster? No. What I'm indicating here is that there's only one thing in this relationship that could possibly change if you went faster or slower, and that's the normal force. Now, look, this is the part where you guys have trouble, and I don't know why. So please actually listen. Like for maybe just clear everything else out, all the other garbage you're thinking about. Depending on how fast we push it here, determines how fast it's going there, correct? If I push it faster here, it'll be going faster there. I can decide how fast it's going at the top of the ramp by how fast I push it at the bottom. So I can make it go any speed I want. If I need to go faster, I just push it harder, correct? But if I push it too hard, it's going to fly off. It's not going to stay on the track. We're trying to make sure it stays on the track. Now, I'm saying this to you because we can adjust this number. We can make it bigger, or we can make it smaller. We can't adjust this number. It's going to stay the same no matter how fast I push it, correct? So if this number gets bigger, something over here has to change so that this side can get bigger, because these two things are equal. Right? The left side and the right side are equal. So for the left side to get bigger, n has to get smaller. Right? It's the only way the left side can get bigger is if n gets smaller. Do you guys see why that has to be true? Right? Because if this side gets bigger, this side has to get bigger. And again, the only way the left side, this side, can get bigger is if n gets smaller. What's the smallest n can be? 0. Because the normal force can only push up, it can't pull down. So the smallest it can be is 0, which means if the left side, the biggest the left side can be is when n is 0. So if I make n 0, that's as big as the velocity can get. The velocity can't get any bigger because the left side can't get any bigger. If the velocity gets bigger now, it's airborne. It's no longer traveling in a circle. Because the only other thing that could start to happen is the path will then begin to change. It will no longer be connected to the surface. It's going to go like that. That's what we talked about first semester. So the result is we set n equal to 0, and we find that V max will be the square root of GR. That's the algebra. You guys can do algebra, and this is in your notes. We did this exact problem at least 5 times in here. This is now number 6. So, come on, guys. Be able to do this. There's 2 versions of this question, if you'll recall. There's this version, and then there's the loop-de-loop version. They're similar, and then they behave in a similar way. But this isn't the question I want to ask. What I wanted to ask you is how fast can you start the ball so that it doesn't jump the ramp? Meaning, what's the biggest I can make this velocity so that it still makes it over that hump without leaving the surface? There's a carnival game like this. There has been to the carnival and had the bowling ball, and you got to push it up the little ramp and make sure it doesn't come back to you, one of those. This is similar to that. So what I'm asking is, what is the fastest we can push it at the bottom so that it does not leave the surface at the top? And we did this problem too first semester. We added this when we did energy. That's how I know we've done this problem more than once. This is the third version of this problem now that we have spinny stuff. And you guys should know how to do this. Let's see if you can, but I'm expecting great things now that we did this part. And now that you're all real smart and you know things. So how can we tell that this is an energy question? What's the big giveaways? We're asking about a velocity. That's the first giveaway. What's the next giveaway? There's a clear change in height. That's right. That's the big giveaway that this is an energy question. So let's do the energy question. There's going to be a bottom energy and there's going to be a top energy. Work it out. See if you can just write out the skeleton of the equation. I mean, what things am I going to have to include? What kinds of energies? Okay. What kinds of energy do you think this object has at the bottom of the hill? I don't know if I can hear you over the rain. Kinetic. Okay, so we have two different kinds of kinetic. We are rolling the object clearly. So do we use both kinds or just one kind? I'm not trying to trick you. I'll remind you. If it's spinning, you use the rolling kind. But there's conditions on the translational one that we have to be a little more careful about. Is the center of mass changing location? Is the axis of rotation in one place? Or is the axis of rotation moving? So if the axis of rotation is moving and the center of mass is moving, then we have to use translational kinetic energy too. So it's got two kinds. It's got 1/2 mv squared, and it's going to have 1/2 I omega squared. It has both kinds because it's rolling. Look, the moment somebody tells you something is rolling, it's always going to have both kinds of energy. So if you just want to commit that to memory or put that in your notes, that's a good thing to put down. Rolling will always have translational and rotational kinetic energy. Don't have to think about it that much. Go ahead. Okay, so it's an and. So both things have to be true. The first thing is that the center of mass has to be moving. The second thing is it can't have a fixed axis of rotation. All right. Good job. But now we're going to the other part. So let's see. Person number 18. Excellent, Ava. What do you got for me? What kind of energy do we have at the top? What's that? I think we're going to have gravitational potential energy. Yep. What else? Is it moving at the top? It has to be moving. We found out how fast it has to be moving. That's the whole idea, is we're trying to see how fast we can push it so we can not jump, but we are going to be moving up there. So what kind of energy does that suggest? Again, don't think I can hear you over the rain. Yeah, which one? Okay, what else? Is it still spinning? Well, keep in mind, if the storm's too electric, we get to have an extended 7th period. Oh, have you guys never been? The bare bones thing here, but we have to make a decision now, because I haven't talked about this yet, but we need to make a decision. What kind of round thing do we want this to be? We have to choose one for the problem. Do you want it to be a disc, a ring, a ring? Okay, so it's a ring. No, I'm letting some of the people who had to answer questions decide. So it's a ring. Sorry. All right, so if it's a ring, what's the moment of inertia? That's right, 1 mr squared. Now, folks, there's still some stuff here, and I know we've got the storm, so here, I'll make sure that you guys can hear me. Oh yeah. Be ready. Now everybody can hear me. More importantly, I can drown you all out, so that's good. Don't tempt me. I got a volume control right here. Now, I want to walk through this, and I need you guys to kind of be with me on this because I know it's hard to hear, and I know it's weird. Rain in Florida. You guys get so weirdly spun up when it rains, even though we live in Florida. It rains all the time. You have to make some substitutions here. Start making the substitutions. You know what they are. There are some ones that are going to be weird. So let's handle the I and the omegas first, because I think that's the easy things to do. So start. I'm not going to do it. You do it. That way I can come and take a look at yours and call on you. So make the substitutions. I would say that put a B here to indicate bottom and a T here to indicate top. So we have a way of differentiating that, but just start making your substitutions now. To stress you out, I'm not trying to trick you. What you have to do now is procedural. Write the procedure down maybe a couple times in your mind or on your paper so you can find it tomorrow and you don't have to say, I don't know how to do it again. Look, you're going to substitute something in for I. We do it a lot. So we know what to substitute in for I. Next, the system is rolling. Rolling is a condition. It's a condition. You're going to substitute that in. Stop making me tell you how to do this. You guys are not helpless. So on this side, 1/2 mv bottom squared plus 1/2, what do I put in for I? mr squared times, what do I put in for omega? V over r squared. That's right. Now, this is V at the top, this is V at the bottom. Now, I don't want to be this person, but I'm going to be for a minute. These R's stand for what? The radius of our ring, correct? What's this R stand for? We understand that's a different R, correct? Yeah, so maybe we should, I don't know, use a lowercase r here, just so we know it's a little different. Yeah, this one for V, because this is how fast it's going. And that means this 1.5 is the r, because that's the radius there. By the way, can somebody tell me how high the object's going to be when it makes it to the top of the little hill? Isn't that also little r? So we could change h here to little r, since that's how high it's going to be when it's at the top of that hill. Do you see why I'm doing that? Because r and h are the same thing here. Remember, these are just placeholder variables, and sometimes there's going to be some overlap. Now this next thing is pretty easy. You just cancel out the r's and stuff. You know, this is going to be 1/2 mvb squared plus 1/2 mvb squared. This will be mgr plus 1/2 mv top squared plus 1/2 mv top squared. Have stopped for a moment. Aw. Now, we don't have much time, but we can finish, and I want to. You can see the things that we can combine together, right? So, I want to show you something, because this comes up, not infrequently. So, do you have something that looks like this? We're going to cancel out all the m's because they're the same. But we know what VT is. That's the max velocity from earlier. So look at your notes. What is Vmax? Yeah?
How can we cancel out all of the m's?
Because there's one in every term. It's not about the number of m's. If I multiply both sides by 1 over m, right, we would distribute. Okay. Now, again, do you remember that V max is the square root of GR? Use that, because we have a GR here already. If I put that in for VT squared, I'll have square root of GR squared. Do you see it? I'm just doing some substitution. I know we had numbers, but sometimes working with the letters gives us an easier approach to the number side. This side's just going to be 2GR. That's it. What is R? It's 1.5, right? And we know G, what's G? 10. So if we want it to make sure it doesn't go around the top, that doesn't leave the track, we better push it slower than the square root of 15, which is just a little less than 4 meters per second. If we push it any faster than that, it's going to jump the track. You're right, I can't do my arithmetic right. It is the square root of 30. So I better correct that.